Hello everyone and welcome to this live stream. My name is Laura Mol and I work for Studium Generale, the platform for knowledge and reflection of the Utrecht University. You're here today for the second lecture in the series A Grip on Time, a series we organize with the Faculty of Science, the Faculty of Humanities and the Faculty of Social Sciences. I want to welcome everyone watching this live at home. I want to let you know that you can leave your comments and questions during tonight's event in the YouTube chat. The moderator will make sure they get to me so we can discuss them with our speaker of today. If you enjoyed this video, feel free to like and subscribe. It will support our channel and we'd really appreciate that. So last week we had an experimental evening hosted by Susanna Bloem, who showed us what the flow of time can feel like and what a truly personal experience that is. So personal that it's often too difficult to put into words what time means to you. She composed some truly beautiful music to help get a grip on that. And today we approach the concept of time from a totally different perspective. Today's guest is theoretical physicist Professor Renate Loll. She works at the Radboud University of Nijmegen and she's a member of the Royal Netherlands Academy of Arts and Sciences, or the KNW. She will address some, for me at least, questions that are mind-blowing, such as what is time and how did the universe start? The answers are, contrary to last week, not personal, and the way we will discuss time today is much less intuitive, if you will. So Professor Loll focuses on a mathematical description of space and time that can answer, for example, a question such as, why does space have 3 dimensions and time only 1? She hopes to combine space and time into one fundamental law, and she uses computer simulations to build model versions of the universe that she compares with Einstein's theories. Renate Loll enjoys a great international stature in the field of theoretical physics, and I'm truly honored that she's here today and willing to share her knowledge. So please give her a warm and virtual welcome. The floor is yours, Professor Dr. Renate Loll.
Well, thank you so much for this kind introduction. Time, of course, for me is very personal, but I will take today a physics perspective as was announced. So time is an extremely rich subject, but this gives us a particular angle, which is not the worst angle, I'd say. So, of course, time is a very abstract notion. It's not a thing, so it's not tangible. But unlike something like, a coronavirus, even our best microscopes will not reveal what time is, because again, it's not a substance, but a concept, but nevertheless an extremely important one, not for us generally, but definitely also in physics. Now, for most practical purposes, even for the working physicist, an excellent definition of what time is what is measured by our clocks. Now, clocks have been with us for a long time, not exactly in the time we are used to today. So the first time measurements were these water clocks that date back to, almost, 3,000, by some people's account, even 4,000 years, of which I'm showing here an example, an Egyptian water clock. So what you would do is, for instance, at sunset, you would fill this up, and then there's a little outlet here at the bottom. As the night passes, you would measure time by the rate the water flows, drips out. Now, that's not a very accurate way of measuring time, it turns out, because it's very sensitive to the temperature. Now, of course, we've advanced very much since. There is a famous story of Galileo Galilei, who, as a student in Pisa, his hometown, was sitting one day in the cathedral and watching one of these very heavy metal lamps, you can still see that today, swing back and forth. And it occurred to him, not just occurred to him, but he measured using his own pulse that the pendulum seemed to have a very stable period. So it would swing back and forth very, with the same time period. Never mind the amplitude or the angle. I mean, how far it swung. And in his very late days, he actually made this insight into a pendulum clock. So the sketch of which you see here, it was never built, or it was built later. So he was more of a theoretician than a practical person. But nevertheless, this was the origin, the theoretical origin of what became an extremely successful next way of measuring time with these pendulum clocks. So again, the idea is really, a pendulum. You can think of a stone suspended on a piece of string. The theory behind it is that if it doesn't swing too much right or left, the time period is always the same. So it's a very much more accurate way of measuring time. Of course, since those days, we've progressed much, much further. And these days, we have extremely accurate atomic clocks. So here, well, you don't see very much what's happening. What one is using in these clocks is one uses really the fact that atoms, that contain electrons, can be in different states, in different energy states, and they correspond to, an electron hopping from one energy level to another one, and that defines a certain specific frequency. And our today's time standard, that everyone uses, is actually defined in terms of the characteristic frequency of such a so-called hyperfine structure level of the cesium atom. Now, that's not very intuitive, but it gives rise to an extremely accurate way of measuring time. So this is extremely accurate. It's 1 part in 10 to the 18. So what does that mean? Well, a clock runs in the entire lifetime of the universe less than a second off, potentially. So that is just amazing accuracy. Now, being able to measure time, to what extent does it also give us insights into the nature of time? So what time is? Well, certainly it highlights some issues about time. If you think of these 3 totally different devices that I mentioned to you about, keeping time, they are all related to motion of something. So be it, the water flowing out of the vessel, be it the pendulum swinging back and forth, be it the atom kind of vibrating at specific frequency. It all involves things moving. That, of course, gives rise to the question, okay, if I was in a situation where nothing moves because it's kind of frozen in, or maybe whether I just know things around, would also time cease to exist or lose its meaning? Now, that's a very interesting question. But another aspect that this highlights is, if we want to understand time better, we need to understand what I would call laws of motion. And these are, of course, central laws, fundamental laws, of which we have already uncovered many in physics, and probably will uncover more. Now, if you can control motion, if you can describe it theoretically, then that gives us somewhat of a grip and better grip on time. The better we understand that. Now, describing things quantitatively really in physics starts with classical physics. So the physics of Newton, Newtonian mechanics, as you've perhaps also learned it in school or even in university. Now, the concept of time now becomes a quantitative concept. We formulate laws of nature that are quantitative, not they just don't say, oh, certain things happen. No, they say, okay, my ball is in a certain position at a certain time. I throw it away with a certain velocity, and it arrives at another point, which I can compute with my laws of motion. Now, what are relevant forces that drive motion? Well, there can be various. We know, of course, of 4 fundamental forces in nature. So let me just talk about 2 of them. The electromagnetic force, if you know, between charged objects, particles, different opposite charges attract. equal charges repulse, uncharged things remain neutral, not in motion. That's not what we're interested in. Now, but gravitational force also causes motion. For example, it forces the pendulum of that clock. Once it has swung to the end, what forces it back is, of course, the gravitational attraction of the Earth. And if you are thinking about the moon in its orbit around the Earth, that's also kept there by the gravitational force that the Earth exerts on it. So these are forces, and our laws of motion describe how things move under the influence of these forces. Now, where does time come in when we formulate the laws? Well, if you're thinking of, ideally some point-like object, well, its position is described by 3 numbers. Why 3? Because our space is 3-dimensional. So I have to give you, if I imagine kind of a coordinate system in space, I have to give you 3 numbers in order to locate this object in a unique way. And what a law of motion is, it tells me, again, if I throw or set something in motion with a given velocity, which I call v here, it will then arrive, it will have a trajectory in space that is some x, y, z as a function of t, and that will describe me anything I would ever want to know about that motion. So I formalize this with a notion that I have already used, kind of a coordinate grid, right? Of course, if I look at space, there are no points anywhere in space. There's no coordinate grid there, but this is what I use to theoretically describe that situation. Yes, I imagine now this ball, and it stays in a plane, so I can ignore one of the 3 coordinates, and then here I monitor it, and at each moment in time, say I decide to measure some units of time, 1, 2, 3, 4, 10, here in green with my stopwatch, and I monitor its position in x and y direction as a function of this time. So this coordinate grid is important here, and there is some kind of external time which requires some measuring device. And this is how time appears in the classical laws of mechanics that would regard something, will describe how things fall, how things move. Again, the moon around the sun, for example, the pendulum here. This is all really part of what we call Newtonian physics. So here is Newton in this very famous portrait, and here is his Principia. This is where he wrote down many of these ideas, kind of mathematical, physical ideas. It's from 1686. And he had a specific view of the universe that then formed the basis of laws that he formulated, that had time in them, that had, of course, space in them, and that were dealing with gravitational force. So like what I just showed you of, objects in our solar system, of balls that fall, all described by gravity. But the essential thing we want to concentrate on is how did he think, or how did people at his time think about time and space? Well, it's really, like this kind of coordinate system that I showed you. Yeah, one imagines, all of space and time can be uniquely characterized, each point there by 3 numbers. And this imaginary coordinate system I can extend infinitely, in either of the 3 directions, back and forth, and there is no structure there. So this is kind of space, what one calls absolute space, absolute and unchanging space. And at the same time, what the laws require, or what transpires also from the way they're formulated, is that there is some universal clock. So that clock is the same for everyone, everywhere. It's absolute, so it ticks everywhere in the entire universe, at the same rate. So these are the concepts of absolute and unchanging space and time. Now, this really still conforms, it conforms very closely with our own way of thinking about, measuring certain spatial distance. I just take a ruler, or some other measuring device. A time interval, from now to later, I measure on my clock. So that's really also in our intuition very closely related, or is basically identical with the time that's present in the Newtonian laws of mechanics and physics. And this is a very powerful way, it turns out, to describe nature. So the mathematical model, if one wanted to be somewhat more abstract, time is modeled by the real line. So the real line is just an imaginary axis that extends to negative numbers, real numbers, or positive real numbers, all the way to infinity, and just describes moments in time. And for space, it's a threefold product of the real line, because one for each of the directions, up and down, back and forth, right and left. Okay, now these are the models of space and time that served us extremely well for about 300 years and even more. Now, what comes after that, what is often called modern physics, goes beyond Newton. And it gives us a quite different view of time. However, I should warn you, these notions have very little to do on the whole with our everyday experience. So they're rather counterintuitive and often refer to very extreme scales, which we are usually not confronted with in everyday life. That's why they're so counterintuitive. And when I put modern in inverted commas, it means, well, this is really physics that's more than 100 years old. And of course, textbook stuff, but nevertheless, it's maybe a good idea to explain some of it, because in some senses, it's as counterintuitive to us as it was to the first practitioners. And of course, the person who has to be named here is Albert Einstein. So his name is very much tied to the theories of special and general relativity. So let's do the special one first. That was written down in 1905. So that's more than 115 years ago. So let me call this the first relativistic revolution. And it really is a revolution in our way of thinking about time and space, because here I summarize it very briefly in this equation. Time plus space really has to be thought of as one entity, which we call space-time. So how does this come about? Well, an illustration to make things short or make and also somewhat plausible is what's called the twin paradox. Now, what is the twin paradox? Well, I don't know why people appeal to twins. We like to do this, but let's imagine these are twins. So here's the guy, here's the girl. So they start out at the same time. The guy stays at home on his sofa, not drawn in the picture, while his sister takes off on a very fast rocket and goes off to the nearest star, Alpha Centauri. Very, very far away, but she has a very, very fast rocket. And then eventually, she doesn't land, so she returns back home. And what she finds is that she is much younger than her twin brother, who stayed behind. The clock for her time has passed much slower than for her brother, who stayed on Earth. Now, this sounds like science fiction, but this is what special relativity says will happen. So what's the reason? Well, it turns out that just the speed of travel relative of these two people, so the gigantic speed with which she's traveled, makes time for her go slower. And that's part of real life. So it's a measurable effect, But of course, part of my previous health warning was to say, well, this is more like a Gedankenexperiment. You need to travel in order to find a measurable effect. You would need to travel very close to the speed of light. And well, although in principle that should be possible, there are no devices we know of that could do this. Why is it called the twin paradox? Well, not because of this very interesting effect that traveling fast keeps you young, but the seeming symmetry of the situation. You know, there's a relative speed, so why doesn't the brother relative who's also traveling relative to his sister, well, he's moving at a different speed. There's a huge speed difference. So why is it not a symmetric situation? Why is she the one that keeps younger and he doesn't? Well, the answer to that paradox is also easily explained within special relativity, has to do with the fact that, well, everything stays the same, of course, but she has to accelerate in a very strong way, something that he doesn't have to do. So the situation is actually not symmetric, and that resolves the paradox. But what this underlines should be the following. Time here depends, as we physicists say, on the observer. So on the person, yeah, that's traveling here. So it's not something that can be said to be universal and unique. Yeah? So that goes against Newton's way of thinking about time, but it depends on the state of motion, in this case, the velocity of the observer. So time, and it turns out also spatial distances, are not universal, but they're kind of relative. They depend on your state of motion, how fast you move. Now, does that mean time and space, you know, as concepts kind of go out of the window? No. Even according to special relativity, there are some things that all observers agree on. These are not separate space and time distances or intervals, but something that's called a space-time distance. So that's not a very intuitive notion, but it's something that combines time intervals and space intervals in a particular way. And that is a feature of a four-dimensional space-time. It's a distance in a four-dimensional space-time continuum. And that's what we then call space-time. And that appears to be, from how the real world works, the true and more fundamental notion than time and space separately. So you really should think, and you know, all of physics as taking place in space-time. Well, that's not so easy to wrap one's head around. So what is a mathematical model? What has changed compared with Newton's idea? So with Newton, we said, okay, for each point in space, we give you 3 coordinates, and there's some separate things that's called a time, and that I denote by t. Now, what space-time is, you should think of as adding to this coordinate system I drew kind of another axis, another dimension. Of course, it's very difficult to realize in a two-dimensional drawing, but it's meant by putting this green arrow here. Yeah? So a point in this four-dimensional space-time is what one calls an event. So it's something that happens at time t in the point denoted with coordinates x, y, and z. So it's still kind of the same idea. You have a kind of coordinate grid that's there, that is just a stand-in for a space-time that just happens to be there. And again, it happens to be infinitely extended and, you know, never-ending, now both in time and in space directions. But the crucial thing about special relativity says, well, we cannot really make a clean distinction between time and spatial directions. And therefore, we have to combine everything into a space-time. And the mathematical model for this is a fourfold product of the real line. Now, interestingly, some good old Newtonian aspects are still with us in special relativity, namely the fact that space-time is just there. is actually, it's a kind of a structureless kind of continuum. It doesn't change, and it's infinitely extended, as I said. The laws of special relativity tell us in concrete and quantitative terms how to relate time and space measurements by one observer to those of another observer who is in relative motion. So like the two twins. So they give us all kind of the rules of how to get from one to the other. And they also identify the quantities that all observers would agree on. And they have to do with space-time. Now, in order to not get confused, note please that a time direction is still, even in special relativity, different from a spatial direction. And that comes from the very fact that, say, in a space direction, you can go back and forth. Whereas in the time direction, you cannot go back and forth, you can only go forward towards the future. Yeah. So there is still a distinction, but the point is there's no sharp distinction, where kind of time stops and space ends. I admit that unless you're trained in physics and mathematics, it's a little bit difficult and abstract concepts to wrap your head around. But nevertheless, I'm here to give you a flavor. Now, what's also interesting about thinking about a unified space-time and kind of having just one more direction, which I call the time direction, is that we can think of ourselves as moving in the space-time along what is called a world line. So what is this? Now, from my previous picture here, I've suppressed now two of the space directions, y and z. So let's imagine I'm walking along a one-dimensional line, which which is the x direction. So I don't go right, I don't go up, I just keep going straight or back. And then you see this is a kind of an x and t for time diagram. I'm moving here. At each time t, I'm at a certain position x. So you can see here, this is someone who moves a little bit in the positive x direction, not completely uniformly as a function of time, but nevertheless, of course, forward in time. And this traces out a world line. So if you like, each of us has a world line, where they're traveling in three-dimensional space as a function of time. And you can think of it as an object in a higher dimensional, four-dimensional space. So what I've also drawn here are light cones. These are the directions along which light propagates. And since nothing can go faster than the speed of light, it follows that each world line of a real thing, a real person, a real particle, has to lie inside the light cone. But that's just an aside. Okay, so again, this is not particularly intuitive, but it seems to describe reality. So all of our understanding of particle physics, say the way we operate particle accelerators, where now very high speeds appear that make all these effects relevant. Yeah, that's part of physical reality over a wide range of distance and energy scales. So this describes how the world is. That's of course not the end. I talked about a first relativistic revolution, but there's a second relativistic revolution that has a strong influence again in how we think about time. Now, time, of course, continues to be a part of space-time. And this is again due to Einstein in the first place, who wrote down the theory in 1915. Now, the key statement is space-time is not rigid. So it's not just this, structureless thing that just sits there and is, like in the Newtonian sense, universal and unchanging, but it is dynamical. And what brings us to dynamical space-time is the understanding that gravity, the effect of gravity, what we think of usually as gravitational forces, have an influence on the structure of space-time itself. So if we take into account effects of gravity, we must change our idea of time and space. Since all forms of mass, heavy things and also energy deform space-time. Of course, the most beautiful example of a deformation of space-time is given by gravitational waves, which of course were directly detected for the first time only a few years ago. So here is this little picture that illustrates what happens when somewhere very far out in the universe, two neutron stars, or there could also be black holes, almost collide with each other, and just shortly before they collide, spiral in a very violent motion around each other, producing an incredibly strong gravitational field that's periodic because it's a periodic motion. And that gives rise to gravitational waves that are ripples in space-time. And that, of course, traveling very, very far, nevertheless could be observed in gravitational wave observatories here on Earth. So here, let me show you the little movie. So we are very close to the two orbiting neutron stars, and these are kind of the waves they produce. And these waves, these ripples, they're not made of anything, of any substance. They really travel through empty space-time. And they are a periodic way in which space-time carries curvature, so a local, non-trivial structure. And this signal, like electromagnetic waves that are produced somewhere, can be just picked up by antenna, if you like, for gravitational waves. So that's one beautiful illustration how space-time itself is dynamical. Another one is how we're thinking about the gravitational field of a heavy object is by bending the space-time around it, like in this cartoon shown here. So let this be a very heavy star. We are observers on Earth, we sit here in front, and the light of some distant object that lies behind this heavy star reaches us. But the light is bent because the heavy object is a mass that bends space-time. And in a bent space-time, well, light rays don't go straight, or rather, they don't go as we would expect them to travel in a straight space-time. And therefore, we see an image, we see it, it's bent on its way to us, but we extrapolate, as we usually do on straight lines, and we can, depending on how the geometry is, we can perceive mirror images of one and the same object. That's a gravitational lens, and that's again a way to illustrate that space-time is now curved. And time being part of space-time, of course, time is also dynamical, changeable, can curve. What does it mean? So here are a couple of drastic consequences for our understanding of time that follow from this dynamical picture. So, in addition to an effect in special relativity, where we found that time, measurement of time, depends on an observer's state of motion, we now understand, taking gravity into account, that gravity has also an influence on time, and namely on how fast our clocks run. And it turns out gravity makes clocks run slower. So when you're in a strong gravitational field, then your clock would slow down. And a very beautiful way of illustrating that is to put an atomic clock on board a satellite that circulates 20,000 kilometers above the Earth's surface, and measure how quickly time passes there, and compare it with the same atomic clock or an identical copy on the Earth. And what you can measure is that it runs 45 billionths of a second faster per day, because up there, Earth's gravity is weaker, and closer to Earth, it's stronger, and it's a tiny, tiny, tiny effect, because also gravity is a very weak force, but nevertheless it's there, and it has been measured. And in this sense, that's one way in which general relativity has been verified. Yeah? And of course, in a way that could not possibly be described by Newtonian theory, because it doesn't know about many aspects of general relativity. And although it's tiny, it has an important influence on our global positioning system. If we would not take both the special relativistic and the general relativistic influence on the running of clocks into account, then the GPS would be going astray within, a few seconds, and over the day it would become inaccurate by kilometers. So these two theories have to be taken into account when we run the global positioning system. So, and of course, we are making use of that on our mobile phones every day. So it's a very practical application of what in the beginning was kind of, theoretical ideas about time and space. Now, here is a more global idea linked to time that comes out of the new general relativistic picture. So if you are thinking really of our own universe on large scales, then that since this can be dynamical, it means if I look kind of at our universe at subsequent moments of time, defined in some way this time, then this space can change shape and it can change its curvature properties from one moment to the other. So our universe, our actual universe, which we have of course been observing through astrophysical observations, appears to be growing. It appears to be expanding. And not just that, it appears to be expanding at an accelerating rate. Now, this is perfectly described by the laws of general relativity and is perfectly consistent. But when it first was realized that a dynamical universe is a possibility, that was shortly after Einstein came up with the theory, it was a genuine shock. People had never considered that the universe couldn't be a static thing. Yeah, could be something that's not static. So it really was a revolution in how one thought about space and time. But again, this seems to have been verified by all observations since. Now, space and time being dynamical opens a whole slew of possibilities. Not only is space dynamical, but it turns out, if it's dynamical, it can actually also shrink, not only become bigger, but shrink. So if we go back in the history of our own universe, this is illustrated by this here, reversing time, then it appears that everything, there was a point, in search of a better name of the event, a single point when everything began, when the universe began, and therefore also when time and space began. Of course, this is what we call the Big Bang moment. So again, this fact is something that general relativity and its laws seem to lead us to inevitably. But of course, it raises a whole lot of questions also about time. So how did time come into being? Was there time before the Big Bang? Does it even make sense to ask the question? Again, in general relativity, it's not that time goes, overboard. No, it's still there, of course, as a concept, but it has a different nature. It still obeys certain, what I call ground rules. So there is a distinct a causal ordering to events that the notion of time in general relativity provides you with. But nevertheless, it's of course very considerably generalized compared to what it was in Newton's time. Now, how do we model space-time now in general relativity? Well, the single rigid coordinate grid, that is no longer a good model. For one thing, because of the curvature that is now allowed, this local structure that space-time can have. So to illustrate it here, are 3 little diagrams of curved spaces. And you see, I've drawn grids on them, but of course, these grids are no longer, well, they go, in this case, they go with the curvature. They are no longer, one grid size. And if you look at this extreme example here on the sphere here, you will see that a single grid doesn't make any sense. So because here at the poles, you see all the grid lines, they are joined in a single point. So this is a very different situation from what these Cartesian infinitely extended grids we were working with. So they don't work anymore for these curved spaces in general. You can still use them locally, but in fact, it turns out, that's what we've learned about general relativity, all the physical and curvature properties are completely independent of these coordinates. We need to use these coordinates to describe where we are locally and what happens locally, but the true physics is all totally independent of coordinates. What is important for us is that there is no global preferred notion of time in general relativity. So that's, of course, completely unlike what happened in Newtonian theory or even in special relativity, where we still had a class of times, namely of all these observers, these moving observers relatively to each other. They're called inertial observers. Here, in general relativity, of course, these observers can all have their own clocks. They measure time locally. The rules of general relativity tell us to relate one choice to another choice, but it's a totally different notion of time. So it's become now very relative, you could say, but nevertheless, general relativity seems to describe nature extremely well. So not only is it a beautiful and geometric theory, but within its realm of applicability, it just works like clockwork. Of course, there are many interesting questions one can ask about the nature of time that it does not answer, and that are even already present in the classical, by which I mean non-quantum theory that comes beyond general relativity. So, just to repeat, what are those? Well, it allows for universes that are not infinitely extended, but they can be finite. So they can be finite in space. So it's possible that space looks like a slice of such a geometry. So it's just closed upon itself. Yeah, we haven't seen any evidence of that, but it may be very large and finite. In the same time, time we have already seen might end, or there might be a starting point of time. Yeah? These are all possibilities that are inherent as possibilities in general relativity and that were not there before. We didn't know about them. We didn't understand that time could behave this way. So another interesting thing, I talked about the world lines before, but they're very interesting theorems that mathematicians have shown who've studied the laws of general relativity that say that in each universe described by Einstein's equations, there are typically many world lines that just end. So there's an end. So here, they end and typically in singularities. So what are those? Well, it seems that if you fall into a black hole, there is a point where there's a singularity and where all these world lines end. Of course, if you happen to be moving, if that happens to be your world line, you might take a very sad end there. Now, what is interesting from the point of view, of time again, well, what happens to the time of that observer? Yeah, where does the space-time end there locally? What does it mean? It seems that one has to transcend general relativity in order to understand what happens in such extreme situations. Now, before I do this, let me just briefly mention to give you a flavor of what physicists discuss controversially in connection with time nowadays. So there is, well, no one really doubts general relativity, but some people ask for more even within that theory. So they ask, well, should our experience that there is a distinguished moment that we call now, and something that we call, or we experience, or seem to experience, like the passage of time or the flow of time, should that have some counterpart in the physical theory? And the point is that in general relativity, that does not seem to be the case. So we have laws of motion that describe, how space-time develops in time. This is how space develops in time, being the solutions of certain equations. One has to fix some initial conditions. That was like the ball that I throw up. I have to give you the initial location and the speed, and then I, will be able to predict where it lands. Same about space and time, according to Einstein's theory. So people are missing there something that makes us special or makes the present special. So I've grabbed actually from a blog post of Sean Carroll, another physicist interested in time, this little illustration that's something that people would like to see, or some people are missing in the physical theories as they're currently formulated. So what general relativity gives us is, as I said, give me the initial conditions at some point in the past, and I solve Einstein's equation, and I tell you what spacetime is going to be then, now, and in the future. So that's what some people call the block universe. So that's schematically depicted here. However, people say, but look, we haven't yet reached, the future. Well, we are sitting here on this blue space, this blue slide that advances. That's the moment of now. And should that be somehow not be distinguished in the theory? For the theory, each point in time, each moment is as good as any other. Yeah. So, but some people would really like that to be represented because they feel, I would say, they want to combine their personal intuition, which combine them with the best of what we know that physics gives us in terms of describing nature. Now, if you ask me, it's a slightly misplaced expectation. So we shouldn't be surprised if our intuition and subjective feelings are not one-on-one reflected in the laws of nature as we write them down. So that's maybe not so surprising because our intuition is a very limited object, a very limited way of trying to know the world. Certainly, it doesn't diminish the theory if we cannot find our own, personal, subjective notions reflected in it. But anyway, people discuss this controversially, and not everyone has the same opinion. Now, very briefly, another thing that people argue about is what's called the arrow of time. What's this problem? Well, all fundamental physical laws of motion we know, including those of Einstein's theory, are time symmetric. What does it mean? Well, every possible solution, every possible universe it describes, for every possible such universe, there is another possibility that is the same universe but with the time direction reversed. So they're both always, all solutions to the equations come in pairs. But our universe does not seem to be time symmetric. So what do I mean by this? Why do people say that? Well, there is what's called the second law of thermodynamics, according to which entropy, which you can think of disorder, always increases. And what is this? Well, imagine, you have a glass, it falls down and it breaks into 1,000 pieces. Well, this you have often observed, but you've never observed the opposite, namely that you have a bunch of, glass, pieces of glass, and they reassemble into a vessel. So that never happens. Or if you let a movie run backwards, of course, you will also see very funny things. So that don't happen in real life. So there seems to be a directionality which can be characterized as growth of entropy. So there is also a physical law that seems to distinguish one time direction. And people ask, amongst other things, well, could gravity provide the answer to this? And then people have put forward a hypothesis about the history of our universe. Namely, they say, okay, we have Einstein's laws. So, they are perfectly good natural laws of nature. If we now choose our initial conditions in a way that the universe, right at the Big Bang, had a state in which this entropy, this disorder, was extremely low, then, well, of course, it could only grow. It could only become bigger because it was so small. And that explains why, today's scrambled eggs won't be unscrambled. Now, whether you like this or not as an explanation, well, really it is not, because what we're saying is, well, we're just choosing our initial conditions in a very specific way. But why are some initial conditions chosen rather than others? Was there an entity who chose them? Well, it doesn't explain really anything. And even if we say, okay, maybe we have to then invoke quantum laws. General relativity is not good enough. Let's look at microscopic quantum laws, and maybe they explain to us why the classical universe started out in a state of very low entropy. Well, that would only move the problem one step, because then you would have to explain why there were certain initial conditions from which your quantum gravitational laws evolved. Well, I think here I would say, unless we discover some new meta law or some dynamical principle that's reasonably unique, we must face the possibility that physics actually will not be able to answer the question of the universe's initial conditions. That's definitely among the possibilities. Okay, now, very finally, my last 3 minutes or so, let's go beyond general relativity. So it has already appeared. I said general relativity is a fantastic theory within its realm of applicability. So that does not include very, very, very short distances or situations where extremely high energies appeared, including those that prevailed at the Big Bang or presumably at the center of black holes. Now, to answer those questions, we need a theory that takes into account the quantum nature of gravity. Now, to cut an extremely long story very short, so here is an artist's impression of what people believe, kind of in a qualitative way, what has to happen to what we think of as a smooth, classical space-time in Einstein's theory, when we examine it at the Planck scale. So that is this extremely small scale of 10 to the minus 35 meters. So that's 0.0000 with 35 zeros, 0.1 meters. That's a regime we cannot explore with current instruments directly. So it's all somewhat speculative. But what one believes is that at that small scale, quantum space-time itself will start undergoing very strong quantum fluctuations. And what this drawing is meant to illustrate is that it will look nothing like the nice, smoothly curved space-times like those of the gravitational wave picture I showed you earlier. And the question is, well, if that is really the case, if quantum fluctuations are so dominant, can in such a situation I still identify a notion of time? Does it even make sense? Does a notion like causal order, an effect, a cause and an effect in some temporal order, does that still make sense? Are these meaningful concepts on these tiny, tiny quantum scales? People also speculate a lot. Maybe I have just some kind of primordial soup, some kind of ingredients, kind of space-time atoms, some people call them. And from them, somehow, by some magic, dynamically, another structure emerges when we move to somewhat larger scales that then becomes eventually the space-time of Einstein's theory, which of course we know is a perfectly good description on large scales. Another interesting phenomenon that people love to speculate about, but I haven't much time or any time to discuss it, are wormholes. So these are kind of shortcuts in time through space-time. See, illustrated by this picture. This slab here, this two-dimensional slice, illustrates space-time, and a regular person would move along space-time here, but the wormhole gives you kind of a shortcut. And if you find the wormhole and manage to pass through, well, you will end up in a completely different place in the universe at a completely different time. These are, of course, totally speculative objects, but a quantum gravity theory should be able to tell you whether they're real or not. So here's my last slide that takes us to the forefront of current research about quantum gravity, which also, of course, involves questions on the nature of time. So research that I and collaborators have been involved over the last 20 years are the development of what one should call candidate theories of quantum gravity, which have very nice properties. They have very few, what we call free parameters, kind of that are kind of things one can tune when things don't quite work out. So very few ingredients and are very kind of hands-on models that produce, amongst other things, quantitative models of quantum space-time near these very, very short Planck scales I talked to you about on the previous slide. And they lead to concrete and very surprising results. The results are concrete because, as was already mentioned in the introduction, they come from computer simulations. And here you see an example of what is a little toy model of a quantum spacetime that is not invented and drawn. It comes out of a computer simulation, and it has very fractal properties. You can see. So that's one way, apparently, in which one way kind of spacetime looks potentially on very, very small scales. So the research program is called causal dynamical triangulations because we build things from little triangles, but it doesn't really matter. The shape doesn't matter. You shrink them away in the end. And one thing this formulation is particularly suited for is to investigate whether it's really true that from kind of very wild microscopic quantum structures with some dynamical mechanism emerges a larger scale space-time that is nice and classical looking, it has all the properties we expect. Is it possible? And what can we say? And give me just one surprising result, because I talked to you about surprises. Well, what comes out of the study of these models are some very robust and generic properties. And one of them is that it appears, if you examine the dimension of space-time. Remember, I was starting out by drawing space-time in special relativity as a four-dimensional coordinate system. So four-dimensional is our space-time, at everyday scales, as far as you can tell. Now, it turns out that when you approach the Planck scale, the dynamics of these quantum fluctuations is such that the space-time there appears to have a dimension that's much lower, 2 or near 2. And it can be partially explained by kind of fractal behavior, but it's something that no one expected, but it turns out that many people find it in their candidate theories. So that's very interesting and might have potential consequences, of course, physically. Now, another thing about emergence, what we found, and not just my group, but many groups have found by studying dynamical microscopic models, is that it seems that time and causal order do not seem to emerge. That means, if I start with a kind of quantum soup of little atoms of space-time and let them interact, and then look at them from a distance to understand their macroscopic behavior, unless I put in already microscopically some remnant of a notion of time and or causal order, we don't retrieve any such notions on a macroscopic scale, which is, of course, needed in order for them to be physically acceptable theories and compatible with Einstein's theories on large scale as they should. So what we conclude, or what one may conclude preliminarily, that time really seems to be needed as a fundamental physical concept on all scales, including these tiny, tiny ones. Now, I can imagine that you are now loaded with information and hopefully have a lot of questions about time, but my time's up. So thank you so much for listening.